And today, I think we'll talk about quite an interesting topic. So how to combine or join or merge polymers and metals. We had a large discussion, what is the right word? Is it merging, joining, fusing, or whatever? Basically, we want polymers and metals to stick together. So this is one of the challenges that we kind of daily face. So our company, just to have a background, has 4 major technologies. So we do plastic injection molding, turning, high pressure die casting with machining, and also electroplating. So just a few numbers to get an idea. I will pass this very quickly because obviously it's engineering presentation. I would say we're a mid-sized European company or a large Slovenian company, but Slovenia is small, so it's a large Slovenian company with just above 500 employees, with around 65 million turnover, and we're located in Kranj, in this close to the center side of our city. And we're more or less present in all major categories in terms of serial production, obviously automotive or especially commercial vehicles being the main one for us, but we're also present in electronics, home appliances, and basically all other areas. And here you can see the usual suspects. I think many of you know our clients. So we are used to work with them. We're used to this serial production process, mentality, and so on. So originally, I would say we kind of come from single component production. So like I said, plastic injection molding, turning, high pressure die casting, and electroplating. But the real added value for us really lays in joining these technologies together. It means hybrid components. So hybrid means combination of polymers, metals, or other materials. You can see the 9 major categories here. So the first one being obviously high pressure die casting and then additional overmolding with polymers, then Zamak casting and then overmolding, shafts first machined and then overmolding of different inserts, bearings, stamped parts, also pins, connectors, again axes or shafts with stator packages and then overmolded, and also overmolding of electronics. So to go perhaps just a few more in detail in certain sections. So overmolding of rotors and stators is one very important area for us, especially due to the different pumps, oil pumps, water pumps, where you need a shaft that gets assembled with the stamped lamellar package and then overmolded with, let's say, PPS, PBT, then overmolded of shafts and then additional magnets insertion, and also overmolding of stamped parts, bearings. Every single of these categories has their own challenges. So just for example, if you overmold bearings, it's extremely important to have enough injection points so that you pre-tension the ball bearing all around so that you do not affect its lifetime. So every single category has its own challenges. Then, for example, overmolding of aluminum cast parts without machining, extremely challenging task because aluminum castings have a tendency to vary in thickness. So very challenging task. Overmolding of sensors or assembled PCBAs. Again, you have an assembled electronics which can only sustain low pressures, not to be damaged. So we use special low viscosity epoxy resins to reach low enough pressures not to damage the electronics. Also overmolding of aluminum with aluminum of different shafts or inserts, and also lastly overmolding of different pins, connectors, and so on. And what all these categories have in common is basically that we always try to bond or to connect different types of materials. And their main problem is that they share no love. They don't want to stick together. They're like an old couple that wants to go apart, and now how to fix this connection, this bond between them. This is a very, I would say, interesting area of research. So this is a very clear picture of what problems are we facing. So basically you have let's say an aluminum casting, then you overmold on top a polymer, but the polymer wants to go apart. And also one of the challenges is that they have different coefficients of thermal expansion. So again, if you heat up the component, the aluminum part will expand differently from the polymer part. So you can compensate that to a certain degree with different fillers, different portions of glass or carbon fiber or other fillers, but never optimally. And this can also be simulated, so all this can eventually be also analyzed in terms of numerical simulations. But still, you get to a point where you ask yourself how we will solve this in the production. So there are different ways. Obviously you can have, let's say, different holes or locking geometry on the castings or on the stamped parts. But if you will talk to, let's say, production worker in the foundry or in the stamping industry, you will see that it's very difficult to deburr such holes or to punch them through. It's a very challenging task. If you do not deburr these holes correctly, when you injection mold the polymer inside, the hot polymer will basically remove some particles of the casting and it will flush them on top surface, which causes then a scrap. Now the other way would be also with glue. But again, gluing is again an unwanted process in terms of CO2 footprint, an additional adhesive or chemical is used to connect them together. So it's not a favorable solution. So in a way to tackle this challenge of combining polymers and metals, we developed or are still developing two technologies. The first one being LaserFusion, and I will first talk about this one, and the other one is SonoFusion, and this is still in the early stages of development, but I still think a very interesting solution that might also be of interest to some of you. So let's first move on to the LaserFusion. So basically what is LaserFusion is the process of using a laser source to modify the surface of the metal part. So why use a laser source? Well, lasers have a tendency to be extremely repetitive. They have a very high repetitiveness. They're extremely precise. So if you take a microscope and look at different structures made by using different types of lasers or different technologies, you can see that on a nanoscale or micro scale, you can get extremely repetitive and very precise geometries. So that's one of the benefits that laser technology offers. The other one is that lasers are being used for quite some time, so they can be either used for removal of rust on surfaces. They can be used, to improve the adhesion between adhesives and the second component, or they can also be used to modify the surface energy, or perhaps to do hydrophobic surface property. So basically, by modifying the surface structure, we can see that we can achieve a lot of different properties of the material without really adding any additional chemicals, just by modifying the surface. So the way we do it, or I would say a simplified physical concept of our technology, is that we use a laser beam, which we focus onto the surface. We then partially evaporate and partially molten the surface with different types of both laser sources and also process parameters. In some cases also surface preparations. We can then modify and get also a negative mechanical locking on a micro scale. So after this process, we then do the overmolding, the injection overmolding, which basically allows us to reach a micromechanical bond on a micro level between the polymer and the metal surface. So if you would take your phone, because phones nowadays have very good cameras, you would see a very repetitive microstructure on a micro level that basically allows the polymer to penetrate inside. Or if you take a bit larger zoom in or magnification, you can see that you get very repetitive micromechanical locking geometries that allow us to really overmold the component and achieve a polymer metal bond. So there are two main use cases that we see, at least in the upcoming future and also already on ongoing projects. The first one being is the combination of, let's say, stamped or cast components with TPE overmolding. So it means, for example, if you have large gaskets, like in this case, if you imagine to assemble this is extremely difficult. It's a thin, long sealing that is very clumsy. If you imagine this in a serial production where, let's say, a worker or an automated cell needs to position this O-ring or sealing on top so that it doesn't get rolled or damaged during the process, it can be extremely difficult. But in this case, we basically pre-prepare the part with the microstructure on top, and then we directly on-mold the sealing. So it means we get much better precision. The tolerances are not summing up because we always use the same reference point. So the both quality, the leakage connection, and also the end result is much, much better than it would be with just standard assembling. So in this case, we used 3 different TPEs that were either on-molded on stamped or cast components. And in this case, we actually used rubber. So a thermoset material that was overmolded over inox steel. The other application that we see also to be used is for structuring of pins or connectors, because there's a quite common problem, especially with pumps, either water or oil pumps, that you get penetration between the pins and the polymer matrix. So even though the pins are overmolded, there is still a small gap during the expansion and contraction that basically creates capillary effect, and it will draw the medium, let's say from oil or water, from the high pressure to the low pressure zone. So it will not be leakage tight. So in some cases you can solve this with, let's say, a plasma treatment, but you are in a way limited to which polymers you can choose. In this case, we can structure the pin on a micro scale again, we overmold it, and by that also improve the leakage tightness. So now if you look at the overall, I would say, process scheme in comparison with first with gluing, and if you want to overmold, let's say, or onmold a TPE sealing on top of a structured surface instead of gluing it. So if you want to glue a component like that, you would normally first need to clean the surface or activate the surface. So for that, you normally use, let's say, a plasma activation process. Then after you activate the surface, you apply the glue, either one component or single component glue. You need to pre-manufacture the sealing and then assemble the sealing on top, which is a very complex, extremely complex task, especially to be really repetitive. Now, if it's a two-component glue, you normally also need to preheat it, which will, reduce the cycle time. But it adds cost because you need an oven, you need some inventory space, so just that the glue hardens. And then after it's finished, you get a finished part, normally not that is not completely hardened. So many times it hardens completely on the way to the customer during the logistics. So in this case, with the overmolding principle, we do the laser structuring process. So right next to the production injection molding cell, and then we directly onmold the sealing, and that the part is with that also finished. So we can already see at this stage how much simpler and also quicker it is to get a finished part made with TPE overmolding. So the other case, like I said before on the previous slide, is overmolding of pins. In this case, we do the structuring of the pin, as you can see here. Again, it's a different kind of structure, but the same physical or same logic is used. And in this case, the competing process will be potting, which I'm sure many of you know. A lot of our customers as well have used or are still using potting. So you basically first overmold the pins, you create like a small groove inside, and then you pour the potting material inside this groove. So basically the potting material creates a leakage tight bond between the pins and the polymer matrix. And then you need also to harden it, and then you get a finished part. Now the problem here is also that potting itself is quite expensive. So potting material is, I would say, around 100 euros per kilogram. Even though you need small dosages, you still need a potting system. Potting material, nowadays when Europe really forces itself to be green and you need all the sustainable solutions, it's not probably the optimal solution. In case of structuring, again, you pre-prepare the pins, you structure them on the surfaces that are overmolded, and then directly overmold, and you get a finished part. So there are obviously a lot of benefits in terms of just how many steps you need to get the end result of the finished product. So obviously how to develop this process, or how we also then support our customers. We basically use two different prototype tools. So the first tool is to produce a tensile specimen, as you see here. This is mainly used to determine different mechanical characteristics, or also to produce thermal fatigue and then do tensile tests. So we structure a surface 10 by 10 on a metal plate. It can be, from copper, steel, aluminum, whatever the customer needs. We structure the surface and then we directly onmold the other half, so the hybrid component, and then to perform the necessary tests. Or in case of overmolding of pins, we also have a prototype tool where we structure the pin and then we onmold or overmold either one component thermoset, one component thermoplastic, or a two component, depending on the customer requirements. So all these possibilities are possible to try out different material combinations. And once these pins are overmolded, we can also perform a pressure test where we position basically the pin inside the rig. We apply overpressure and then measure the leakage. To see if this structured surface does hold the leakage test or not. So these two prototype tools allow us to do the development, but aside of the development process, we also use several quite advanced validation methods. The first one, especially for leakage tightness, is we use a high-speed camera. So, for example, if you see that your part leaks, we perform a high-speed camera analysis where we also see which surfaces are, let's say, lacking the leakage tightness, where the bubbles are formed, how quickly they are formed. So we use different criteria to see how well the structure was or wasn't prepared. The other method is also micro-CT. So we have our own internal CT machine, but for more detailed analysis, we then normally outsource a micro-CT analysis to see if there were bubbles formed, if the microstructure has been in any way damaged locally, where we can really zoom in on a micro level to see how the microstructure behaves also in terms of the fiber orientation. So I'm not sure if you can see quite well, but it's quite visible that you have different fibers. And we also see how the fibers then lock themselves inside the structure. Another method that we also occasionally use is electronic microscopy. In this case, we first, let's say, prepare a microstructure on a steel specimen, which needs to be completely corrosion resistant. So we first do the microstructure, and then afterward, we do the zinc nickel process. And because zinc nickel is a galvanic process, it means it's based on an electric potential. You basically just offset the microstructure. This is then also accommodated in the first microstructure so that the final microstructure will be by an offset of, let's say, 10 microns thicker. And this means that we get a completely corrosion-resistant surface, which is microstructured and can be then directly overmolded. Then we have also other methods, like tensile tests, thermal cycling or thermal fatigue tests, pressure tests, also on this hybrid part, or corrosion tests. So we can really expose these structures with different types of loads, both chemical, temperature, or mechanical loads. So if I would just, in a way, sum up the benefits of this technology or why it could be an interesting solution for some of the use cases that you may have or our customers may have. So first of all, you remove a lot of additional chemical treatments or use of adhesives. So in general, you do not need plasma activation. It can be beneficial, but in some cases it's not necessary, and without it, it's completely the structure works. Again, it really depends on the requirements of the end customer. The other one is obviously reduction of CO2 footprint, again, related to the first point, because it does remove the use of chemicals, and also, laser structuring or laser technology itself is extremely energy efficient and really focuses the energy just on the point where you focus at it. It also allows you a very simplified component design. So normally, if you would want this TPE sealing to stay on top of this aluminum casting, you would need a lot of different mechanical locking geometries, as I showed in the first two slides. A lot of these hose features, which all create a notch effect in the casting or in the stamped part, and that's why you need then a larger part to withhold the loads. In this case, you can have one seamless geometry without any hose, which obviously reduces the weight, reduces the size. Also, the shorter and simpler process flowchart, which I think you also understood what I meant by that, especially in a way we're moving from assembly steps to production steps. It means that we kind of want to reduce the assembly steps and any manual labor in between, but really move onto the consequential production steps, just going from one tool to the other, which also improves the overall quality. And obviously the process allows us a very high process automation level. And again, as I showed in one of the first slides, it also improves both the quality and the process repeatability, because the laser technology itself offers repeatability in the scale of nanometers. And obviously, the one word that always arises, especially in automotive industry, even if you wake up at midnight, you hear this cost reduction. Yeah, obviously, if you plan the production right, and if you use this technology from the product development stage, it will definitely allow you to also to reduce cost, especially in comparison with assembly steps or other technologies that will need many more production steps and may also cause a larger scrap rate. So the other technology that was also talking about, and I think is also very interesting, is SonoFusion. SonoFusion has some similarities with LaserFusion, but the main difference is that in this case, we basically merge or join or weld or however we want to call it, already pre-molded plastic covers with, let's say, an aluminum housing. So why would you need something like that? So if any of you comes, let's say, from electronics development or high-power electronics, will understand that you in some cases when the electronics hit too much, you need some active cooling solutions where glycol goes through an aluminum casing. Aluminum casing, because aluminum has very high heat conductivity, it drains the heat from the electronic source and then puts it inside the glycol or water or whatever the medium is, and then removes it from the system. So in this case, the logic that we use is that we also first we cast the component, the aluminum component, we apply the laser structure on top, and then we do a pre-molded plastic component. We use a welding sonotrode. So if you know ultrasonic welding or the process of ultrasonic welding, we have a custom sonotrode. And then we preheat the structured aluminum surface and we basically weld them together the same way as you would normally weld two plastic components with ultrasonic welding. So the philosophy is the same. Obviously the devil is in the details of this technology, but just to get an understanding what we're trying to achieve in this case. So this is a cross-section for you to understand. So we have a structured surface. So this was one of our first tryouts. And then we bonded the polymer on top with the aluminum structured surface. The flow, again, is extremely simple. So we first laser structure the aluminum component, we preheat the aluminum component, and then we do the ultrasonic welding process on top. So we first started with the proof of concept development, where we used small aluminum cylinders. We did different kinds of structures on top of them, and then we welded them together. First with 3D printed covers, and then also with injection molded covers to see the leakage tightness. And since we got really good results, we are now moving on to a larger prototype. So just for understanding, what is the end goal? So the end goal for us is to design and produce and also validate a component like an inverter housing, where you have an aluminum cast part with precast cooling channels, and then a pre-molded plastic cover that already has pre-molded connectors on top. So these are one of the two, I would say, most expensive parts that you normally need, because normally they're produced with turning. And then we directly structure the surface and weld on top. So the competing technology would be, let's say, laser welding, where you would normally use an aluminum housing, aluminum stamped or cast part, and then weld them together using, again, a laser beam. But you still need two separate turned connectors, which need to be assembled. The third competing technology would be friction stir welding. So I'm not sure how familiar you are, because this is more for people from the aluminum casting industry. But you basically have a tool, like a CNC machining tool, that drills itself inside both the casting and the cover and fuses them together with friction. But you still need then different connectors that are afterwards also assembled on top. And lastly, the process that we definitely want to avoid, and also the competing process, is where you have a cover. You need a lot of different screws, a sealing, again, connectors. So a lot of different manual steps or assembly steps are required to produce a part like that with the same function. So we do estimate, in comparison with this standard procedure, that we can save up to at least 25% of the cost for a production of exactly the same functionality component. And we definitely see that we can be cheaper than also all other technologies, just due to the reason that we need only two components that can be cast and injection molded and directly merged together. So this was in short. I hope it was to a certain degree understandable. You understood my presentation. Thank you. And if you have any questions, you can reach out or let me know.